Oh, maybe not. Okay. Shoot.
Okay, there you go.
It's
okay.
Yeah, sorry.
It's okay.
So yeah, so the Schwarzschild radii crosses over the physical radii. The surface that's producing the light is now behind that wall that we determined is where light can no longer escape. And so now we have an object that is just kind of infinitely sucking things in, and we don't know what's going on inside of it because light can't get in or out. If light goes, well, light can get in, light can definitely get in. It can't really get out in any meaningful way, but it can get out, and I'll get into that later. It's just not the way you think it can. So the first thing is to talk a little bit about Einstein being wrong. For all of his brilliance and the things he did, he had one kind of major issue, and it was when he first made relativity, he thought Schwarzschild was completely wrong about the possibility of black holes, because he thought Schwarzschild had simplified too far by treating the system as non-spinning. So importantly, when Schwarzschild did these calculations, he is taking for granted that this object is still, not turning at all, which is almost never the case with objects in space. Every time you look at something in space, it's probably spinning somehow. So what Einstein said was, well, if these objects are spinning, like when you have an ice skater and they pull their arms in during a spin, they spin faster. As these stars collapse, they too will spin faster, and they'll actually spin such that the star is spinning faster than the speed of light in places. So he figured that the issue would be things are going to try to move faster than the speed of light, and it's going to have to slow itself down. That may be happening. We don't know that he's wrong, but it definitely is possible that black holes can form. He didn't think it was possible. He thought the threshold for the spin would be more than the threshold for Schwarzschild. Now to talk a little bit about the wibbly wobbly timey-wimey stuff, and this is how Einstein was wrong. One really good thing about relativity was this kind of establishing that being in a high acceleration environment is the same as being in a high gravity environment, essentially. And so the image I showed at the beginning actually was from a movie called Interstellar, which probably people have seen. If you don't want it spoiled and you haven't seen it, I guess you can mute me until I'm done with the slide, because I'm going to walk you through what happens in that movie. They land on this planet called Miller's Planet, and it is pretty close to a black hole. And because of that, they're experiencing extremely high gravity. And what we've seen from experience is that when you're experiencing higher gravity, from experiment, is when you're experiencing higher gravity, time runs slower for you. So there's a kind of famous experiment where you had, I think it was Harvard had this big tower, and essentially they had something that saw that there was a difference in how fast time was moving at the top than at the bottom. They've done it with mountains and planes too, but essentially the International Space Station passes through time faster than people on the ground, on Earth. In the movie Interstellar, they were so close to this black hole that 1 hour of time on the planet they were on was equal to 7 years of time on Earth. So these black holes create kind of these extreme relativistic environments. And that's actually pretty true about what would happen if you were that close to a black hole.
Really?
Yeah, I mean, I think they're closer than they could probably get for that, but as you approach black holes, you do weird things with relativity, and it causes your time to move slower. And we think that would be a viable option to kind of do time travel, because 1 hour passing through 7 years is a fair trade if I want to get to the future. The issue is that the closest black hole would require travel at light speed to get there in a reasonable amount of time. And so you're going to be dealing with relativity in that facet too, and it's probably not likely we can do it. But if we could get close to a black hole, we could do some weird stuff. And importantly, it would need to be a high mass black hole, which I might talk about in a second. So the next thing is why Stephen Hawking. He's probably, at least for me when I was really young, he was a scientist who I heard his name said over and over again. I knew he did astronomy stuff, but like Einstein or Galileo, like I didn't really know what it was he did. And so this is what he did. Specifically, he discovered or kind of theorized something called Hawking radiation. So this is another quantum physics tangent, but as much as we like to say that energy and mass can't be created or destroyed, we think and have good reason to believe that at the very least in extremely short time spans, like impossibly short time spans and impossibly low masses and very high speeds, particles can pop into existence so long as they appear with an antiparticle pair. And so what happens is they'll pop into existence. They're called virtual particles. The experiment that actually discovered them was interesting. They essentially pulled like a near perfect vacuum and did some other stuff to these two plates that they then put really close to each other. And they detected a very slight pressure between the plates, which we wouldn't expect if there weren't just particles appearing out of thin. So what happened then is that they exist for kind of infinitesimally small amounts of time, almost no time, and then combined and disappear. And what Hawking said was, well, if these particles can exist, what happens if they pop into existence on the surface of a black hole, on the event horizon? They're moving at light speed, but if one of them is at the event horizon and pointed outward, and the antiparticle is at the event horizon and pointed inward, the one pointed outward escapes, and the one pointed inward gets trapped. And what happens, and this is kind of backed up by some observation of this radiation occurring, and some very minor observation of these black holes, is that mass gets lost from the black hole when the antiparticle annihilates, but the black hole radiates out an equal amount of energy. And so this is kind of the joke I made with the title here, is matter and energy are two sides of the same coin. And what he's saying is the black holes are just exchanging their matter for energy, but in this kind of weird quantum way. And when that happens, we think that black holes can inevitably just kind of fall apart entirely. The last thing is that because we're dealing with high gravity and we're dealing with things with mass, light, you can actually bend light with high gravity environments. If we go back to the image from, other way, from Interstellar, you can actually kind of see it happening. So this glow above and below the black hole, this kind of coming around here is a ring of mass around the black hole, like
Saturn.
Yeah, but it's a black hole and not a planet. This ring isn't actually anything physical in the position it's in now. What it is it's light from the Saturn ring behind the black hole that is getting bent backwards and over the black hole, so it's being pointed at us. So the light kind of takes this like arced trail up off the ring and then sideways over the black hole, and it's because it's so massive. And then the other thing is this kind of dark area where it drops off. Interstellar is such a great movie because they nailed so much of this stuff. Isn't where the matter ends necessarily. It's where it's essentially the line for when the speed of light is the orbital velocity of being around that black hole. And because of that, once you're within that realm, it's likely that the light will stay trapped in an orbit that slowly decays, but can occasionally get reflected back out. So light gets bent and does weird things, and that's why black holes look weird. Another thing is, and it's more obvious in the EHT, and I guess we'll get to that in a second, is that they also will produce these like kind of strong jets out the top and bottom. And those jets can do some weird things because of the Doppler effect. So essentially, well, Doppler effect and a little.
I gotta go to Fate.
Okay.
Yeah,
So,
that's fine. You can just text me.
Oh yes,
All right.
I'm running a little late, aren't I?
No, you fine, Jalen. You just text me, man.
Oh my bad. I just didn't.
Oh
Yeah.
my gosh. I'm sorry, Dante. Go ahead,
No
Dante.
problem. Yeah. So lastly, like this jet, basically relativity and Doppler effect are playing together to make it really bright, and I kind of can explain that in a second. But a few important questions come from looking at these images, and so I'll try to walk through those quickly, and then I got one more slide about some news, and then we can move on. So basically, the questions are: what's happening, and why does it look so grainy, so crunchy? what can we learn from looking at it, and how did we actually make it? So I alluded to last week, the way we made it is that we only can, the accuracy, like the kind of angular size we can see in the night sky, is a function of how big our telescope is. And so we got a bunch of radio telescopes because they can observe at pretty much any time around the world to point all at this one object. And they got really good time synchronization down. And if you can take observations with good time synchronization, you can actually combine them and then act like your telescope was as big as the distance between your satellites. So what they did was they took all these really well-timed observations, combined the data, and made a telescope that was effectively the size of the Earth. So that's how we were able to observe this thing that is normally unobservable because of how small it is. That's also why it's so low resolution, because we're really pushing our limits of what we can see. The next thing is there's that dark hole, that kind of black area. That's kind of what I alluded to before. In this image, we're actually looking kind of top down on the Saturn disk. There's a little bit of a tilt, which I'll explain how we know later, but that circle again is kind of where light starts to orbit as opposed to be able to escape. And then below that is the event horizon or the Schwarzschild. The reason one edge is lighter is because that's kind of where the tilt of the beam is. So the black hole is facing slightly downwards kind of. And because of the high rate that kind of the matter is leaving the black hole in that jet is what we call it, the light rays kind of bend inwards. And when they bend inwards, they become more dense and look bright. So that's kind of a quick rundown on all of the weird things that go on in this image that are interesting about black holes. And what's important is we've proven we can look really deep into space now because we can use this kind of interesting method of observation. The last thing is quick news, because it's kind of relevant but not super, is the star Betelgeuse that I can never spell. About a year ago, just over a year ago, started dimming a little bit. We didn't really know what was going on. We think now it might have been gas or some sort of sun, like solar spot activity, like on the sun. But a lot of people also think it might be a signifier that it's going to go supernova soon. Soon being relative, because these things live hundreds of thousands of years. So we think it should die in the next 20,000 years or so. It's kind of hard to predict when supernovas will happen. And so we don't really know what we can look for to know if it's going to happen. But as someone who was in school, I always heard the snow day rituals you're supposed to do. And so every time someone talks about Betelgeuse in astronomy now, they're all talking about how they wish that it'll go supernova at some point. So I thought, maybe we try the spoon thing and that'll work for this one.
Yeah, that's funny, man.
Yeah. Great. Well, that is kind of the end of what I had today. I know it was a lot, but I tried
No, that was
as
great.
much as I could about black holes in a half hour.
No, that was great. That was great. Please, everyone, give him a round of applause. Show him some love in the chat. That's really cool. So that picture that you shown, that little orange white spot, that is the black hole bending light.
Yeah. So it's bending light in kind of a different way than I explained for the picture from Interstellar. So in this, there is a bunch of matter, a bunch of like gas that is getting blown away from the black hole really fast. And it's because of that evaporation, the Hawking stuff I was talking about before. It's moving so fast that it's experiencing like size dilation. So along with changes in time, when you're in high gravity, you can also have changes in scale. It's how like light gets redshifted when it's passing by black holes, but that's
right.
But because it's moving so fast, it's actually moving like half the speed of light, and it causes the light rays to bend inwards because it's actually bending kind of space-time with how fast it's moving. And so, yeah,
wow,
it's a product of how fast this black hole is ejecting matter.
Any questions about the black hole? No, can you send the yeah. I could send a recording. I know some people got to go to work, but yeah, thank you so much, Dante, man. Thank you again. This was even better than the last one. We really appreciate you really being passionate about this topic. I didn't know that. I just didn't know the Interstellar movie like that. Cause I saw that movie, I didn't know that that was a really great depiction of it, because I was lost the entire time,
Yeah.
but I was lost the entire time.
Yeah. It's
but it was
great
a
up
really
until
really
the
interesting
part.
movie.
Yeah, it's great. It's like near perfect until the part where they start doing like the backwards through time and he's pushing the stuff off the bookshelf. That's a little bit more out.
Yeah.
We also don't know what goes on in those environments, so
Yeah, hypothetical.
we just don't know.
Right,
Everything else,
right,
though, is
right.
pretty accurate.
Wow, wow, wow. Okay, so please, thank you so much, Tanaya, Valencia. Make sure y'all text me. Thank you all so much. And Dante, please let me know whenever you get the chance to send me the recordings, and then we can talk about next week if possible. And just let me know, man. Thank you so much.
Sounds good. Yeah, have a good one.
All right, y'all have a blessed day.
Yep. Bye.
Thank you, Dante. Have a good day, bro.